Okay, that's pretty much it. Um, Solutions, qualitative and quantitative. Qualitative means more of a non-mathy approach. Remember we had the salt crystal dissolving in water? You need to be able to reproduce that. So the two forces, the solvating force and the crystal lattice force are the two forces that work there. So you need to make sure you include that in your description. Okay, a quantitative, that's what we're doing. Which we did yesterday, for example, both working with solids and dilutions. Yeah.
So basically,
The materials used.
yeah.
Yeah. I'm going to cover qualitative acids and bases today in a minute. And then there's a quantitative part as well. But as far as solutions go, the will be on how it crystal dissolves. And then quantitative is all the math we've been doing. That's what you were asking, right? I'll implement those changes to your tests, by the way. That email you sent me. So, do you have a lab today?
Yeah.
Okay, remind me in lab, because I have spare time in lab. Okay, and then gases, the gas lab, you're gonna have two gas labs. One is a dry lab and the other is a wet lab. Next week is a wet lab. After that will be the dry lab. Okay, so the wet lab is going to involve actually apparatus using gases. I'm going to have liquid nitrogen there, and we're going to do some interesting stuff, freezing stuff with liquid nitrogen. We're also going to have a demonstration of how heavy air is. You'd be surprised how heavy air can be. There's something called air pressure, and that's the measurement of how heavy air is. So it's quite heavy, and they measure it in the square inch. So, okay, so anyway, that's what test three is going to be about. And I need to look on practice tests, and I'll make sure the practice test covers these three things. Okay, so let's get into what is an acid and what is a base. Um, let's talk about a base first. Sometimes bases are referred to as alkaline. Alkaline is an old term. It's a alchemy-based term, and we use that a fair amount in foods, probably pharmaceuticals. They'll talk about an alkaline environment. Um, biological systems, talk about alkaline. like a lake is turning alkaline versus acidic versus neutral. Okay, as far as, I'm not going to be referring to the rest of the semester as bases, not alkaline. But just keep in mind, alkalinity and basic are the same. Okay, so there are three kinds of bases: strong base, weak base, and a non-base. Okay, definition of a base is a chemical that disassociates a hydroxyl ion, an OH negative ion. So anything with an OH in it could be a base if it disassociates. If it doesn't disassociate, it's not a base. Yeah,
What is disassociated?
I'm sorry,
What is dissociated? Like,
comes off. Like, when I go to the barber, my hair disassociates from my head. Basically, if you have a molecule and a piece comes off, and usually it's an ion, either positive or negative ion. So thank you for asking. It's a good question. Okay. So, for example, strong base. Sodium hydroxide and potassium hydroxide are the most common strong bases. Sodium hydroxide is called lye. You've all probably heard of lye before. Lye is very, very strong, very corrosive. And it does something to fats, which is very unique. What it does something called, it saponifies the fat. That means it makes soap. So to make soap, you start with a fat. Fats are made up of triglycerides, and then you boil them in a lye solution. And what's left over is soap. Now, we just got done doing a lab in Sac City, and we made soap, part of the lab. And they get to take it home and all stuff. And basically we made ivory soap, very mild soap. Ivory soap is a lye soap based on a very strong lye. And you have to make sure all the lye is used up. If you have any leftover lye, the soap is very stringent. It, you have an open wound, it'll sting and stuff. So you have to make sure all the lye is used up. Now, depending on whether you use sodium hydroxide or potassium hydroxide, you'll get different soaps. One will be soft, one will be hard. Also depends on what kind of fat you use. Whether you use a vegetable oil or an animal fat, give you different kinds of soap. It's real interesting. A lot of people have a hobby making soap, but it's based on strong bases. And typically there's sodium hydroxide and potassium hydroxide. Interesting story. When the pioneers crossed the country, like on the Oregon Trail and all that stuff, they made their own soap. The way they made their own soap is whenever they would slaughter a pig, they would keep the fat, and then they would make sodium hydroxide and potassium hydroxide in a campfire. Because if the ashes left over, if you put those in water, it makes lye. So they use the ashes from campfires and the fat from pigs to make their own soap. So kind of interesting. Also interesting regarding soap, the Romans, when they were conquered by the hordes from the north, they lost the ability to make soap. So the Romans were known to be very clean, their baths and all that stuff. But anyway, they lost the ability until the Middle Ages. They regained the ability to make soap. Yeah.
It's alive.
Lye. Lye is not good for your body. Because you know what?
No, I mean, somebody been over
Yes, what happens is it creates soap from their bodily fluids. Now, if you ever, ammonium hydroxide, ammonia, is a very common cleaning agent around grease. Ammonia is a base. So what happens when you clean around bases with ammonia, it turns the grease to fat. And then you can wash it off with water. Now, there's two kinds of cleaning sprays. One is for windows, has no ammonia in it, and the other is for kitchen stuff with ammonia in it. And that assumes there's grease cleanups. So don't get the two confused. So use the window-based stuff on windows, because presumably there's no grease on your window. If there's grease on the window, then use one for your kitchen. Another interesting thing about ammonia water, it's a great pesticide. It's very cheap. I use it for getting rid of two animals in my kitchen, flies and cockroaches. It kills them like that. I have put it in a spray bottle and I have a fly swatter and I spray them with this stuff and they now you can make it yourself at home. You buy Parsons ammonia, it's like $3 a bottle, and you can make 20 bottles of the spray stuff. Or maybe not 20, maybe 10. It's still very cheap. What you do is you put about this much in the spray bottle, and then all the rest is water. Works really well. Flying insects, you go, and they fly into it, drop to the floor, and they start moving very slowly. So you can either, or just spray them some more. Works really well. And it's cheap. It's like 20 cents per spray bottle. And the cool thing about it is to make ammonia water is ammonia is a gas, NH3, and you bubble it through the water. And then it sticks to the water molecule itself. It becomes NH4OH. However, when it starts to dry, the water evaporates, and so does the ammonia gas in the residual. So you're left with nothing. It's totally non-toxic. It works well. It's cheap. It's got all the right stuff going for it. Keep that in mind when you have to buy. And some of these spray pesticides are real expensive, and they don't last all that long either. And they're toxic as heck. Okay, so now let's distinguish between a strong base and a weak base. Strong base means that 100% of the sodium and hydroxyl ions leave the original molecule. So there are no NaOHs left. They're all Na pluses and OH minuses. With a weak base, not 100% disassociates, only part of it. So from 1 to 99% disassociates, depending on how weak or strong the base is. So for example, with ammonium hydroxide, that's the stuff you mix when NH3 and water mix together. About 30% of it goes over to the hydroxyl and NH4. All the rest of it is NH4OH. And a non-base, because it has an OH on it, for example, who's heard of ethanol? Okay, that's called drinking alcohol. Vodka, ethanol, 50% ethanol. Okay, this has got an OH on it, but it's not a base because the H doesn't disassociate or come off. So strong base, it all comes apart. weak base, part of it comes apart. Non-base, none of it comes apart. Now, there's an analogous acid. So we have strong, weak, and non-acids. Acids, they dissociate an H plus ion. So if 100% comes off, it's a strong base. There are 7 strong bases in the world. You're going to run into probably 2 in your chemistry. Unless if you're taking 1A and 1B, you'll probably talk about nitric acid as well. But normally you're going to talk about hydrochloric acid, HCl. It's called muriatic acid. If you're dealing with pool acid is hydrochloric acid. This is acetic acid here. Acetic acid is a weak acid. It's also called vinegar. 5% acetic acid in water is called vinegar. Now that's a weak acid, so only part of it disassociates. So you've got, here comes the H plus, and then whatever's left over will be over here. So you've got strong, weak, non-acids as well. Very analogous to the bases. Okay. There are 2 parts to an acid and a base. One part, let's talk about acids. There's the acidic part, which is the H plus, and the other part, what's left over, is called the conjugate base. Conjugate base. Okay. Now, what's interesting, what if a molecule has an H and an OH in it? Like water. Water is both an acid and a base because it disassociates H plus and it disassociates OH minus. So it's both an acid and a base. Now, it's a very, very weak acid and a very, very weak base. Now, as far as taste goes, acids are sour, bases are no, trying to think.
Bitter?
Yeah, they're probably closest to bitter. So I made spaghetti sauce last night. Tasted it. I wasn't sure it tasted. I didn't like the taste. It was okay, but it wasn't great. And I was trying to figure out what was wrong with it. It ended up being not enough acid in there. So it was tasting bitter. So I added a little bit of rice vinegar. Fixed it right up. So you got to have the right balance in foods. When you make a vinaigrette, okay, the main components of vinaigrette are oil, vinegar, usually water, a little bit of water. And the vinegar has that sour taste and it offsets the fat. So my spaghetti sauce had a half a cube of butter in it, or I should say half a stick of butter in it, but a lot of fat in there too. So the acid also balanced out the fat in the spaghetti sauce. So cooking's got a lot of chemistry in it. It's kind of fun doing that. Okay, now who has heard of the term pH? Okay, most of you have heard of the term pH, and what it is, it's a metric for looking at the strength of the acidic component. So there's a little p, big H. Then there's also something you probably haven't heard of, which is pOH. Now, we're not going to do pH calculations in here, but this is the definition of pH. It's the negative logarithm of the hydrogen ion concentration. That means you have to use your log key on your calculator. And it's the negative log. So low pH is acidic, high pH is alkaline or basic. So if you have a pool or a spa, you test the pH all the time, and you test it colorimetrically, and you compare it to a color scale, and it'll tell you what the pH is. And then you add different things to adjust the pH to what it's supposed to be. Now, the ideal tap water pH is non-acidic. Non-acidic. The reason for that is if it's acidic, what happens does it leaches out stuff from your pipes. Flint, Michigan, that was Flint, Michigan's problem, is their water was acidic. Acidic. So an older house is going to have a lead pipe in it, and the lead pipe is where the pipe from the street comes in and joins the plumbing of the house. And the reason why it's lead is because lead is soft and you can bend it. Because the angle of the pipe coming in from the street and your plumbing in the house is never perfect. So you just move the lead till it fits. It's called a lead gooseneck. If your water is acidic, it'll leach out the lead in that lead gooseneck. Lead is very toxic to mammals. What it does is it binds up with an amino acid, and if the amino acid is in an enzyme, the enzyme stops working. So it's really bad. It includes mercury as well, any heavy metal it works with. So you want to keep your pH of your potable water, the water you drink, slightly on the basic side. So as far as pH goes, pH 7 is considered neutral. So pH greater than 7 is basic or alkaline. pH less than 7 is considered acidic. So you want your pH to be like 703, just barely on the basic side. Now, when you get into 1A, probably 2A, you're going to be doing pH calculations. Yeah.
Isn't like your skin has pH, and that's why like certain pH react to a specific person more so than others. So like I might be wearing the same perfume as Leah, but it can smell differently on me than it does for me because our pH on our skins are different.
That's right. A lot of fragrances have are called aldehydes, and aldehydes change their chemical composition based on pH. So that's one reason. Same with foods, fragrance and foods. The pH will radically change.
Is that the same reason why like some say cilantro tastes like salt because like their pH in their mouth is different than other people, or is that just like
Say the first part.
cilantro? Some people say cilantro tastes like salt to them or goat to them.
Well, yes, no, that's a genetic thing. Yeah, I love cilantro, so I'm glad it doesn't taste like soap. Yeah, it's a genetic thing. Very interesting. the, whenever you're working around, basic stuff and you get a little bit on your hands, you'll notice it's slippery. And the reason why it's slippery is because it's saponifying the oils in your skin, turning it to soap. And soap is slippery. That's why it's slippery. So you can actually close your eyes and you can identify whether something is acidic or basic just by feeling it with your fingers. If it's slippery, it's basic. If it's not slippery, it's acidic. Oh. Okay. Now, with acids and bases, there's something called a neutralization reaction. For those of you who have lab today, some of the double replacement reactions are acids and bases. So when you mix an acid and a base together, the H and the OH form water. And what's left over is called salt. So if you're mixing hydrochloric acid and lye, sodium hydroxide, you'll end up making table salt with lots of heat. Neutralization reactions give off lots of heat. The reason they give off lots of heat is the potential energy in the acid and the base is converted to kinetic energy. And kinetic energy in a molecule is called temperature or heat. Now, there's a lot of calculations when we are dealing with acids and bases. Let's do one. In my summer class, I had a whole bunch of students that already had chemistry. They were from the high school. And so we did a lot of pH related stuff. Okay, the main thing is pH is a measurement of acidity and alkalinity. The lower the number, the more acidic. The higher the number, the more alkaline or basic it is. Okay, so let's look at a problem here. So say we have say we had 4 liters of 3 molar hydrochloric acid. Now, if you look at the reaction for hydrochloric acid, because it's a strong acid, it does that. So this is balanced. So that means the coefficients are all 1. So if we know how many moles of that we have, that's equal to the same number of moles of that as that. So and that's so because the balanced equation has coefficients of 1. Now, sometimes your acid may have 2 hydrogens that come off, or 3 hydrogens that come off. For example, sulfuric acid has 2 hydrogens that come off. So that means so in the case of, this is called diprotic, monoprotic. Protic refers to protons, and an H plus is a proton. So a diprotic acid, 2 hydrogens come off or dissociate. With a monoprotic, 1 comes off. Phosphoric acid is a triprotic acid. How many H's come off of phosphoric acid? I said phosphoric acid is a triprotic acid. 3. Tri means 3. So that's why it's important to always write the balanced equation. Then you know what's going on. Okay. So the question on this problem here, so what is the hydrogen ion concentration? Now, the higher the H plus concentration, the stronger the acid will be. Okay, well, we know that moles of HCl equals the moles of H plus and the moles of Cl minus from the balanced equation. So if we multiply, remember from yesterday, concentration times volume equals moles. So we've got the concentration, we've got the volume, we can calculate moles of H plus. So what we're going to do first is we're going to have concentration is 3 moles per liter in 4 liters. So that's equal to okay, so that means that's 12 moles of HCl and now this is from the balanced equation. It's 1 to 1 to 1. Okay, so what is the concentration then of H plus in here? Okay, we've got moles. Remember, square brackets is concentration. So the concentration of H plus is 3.0 moles per liter. And the reason why it's the same as HCl is because it's a monoprotic acid. So everything in the balance equation is 1, 1, 1. And while we're at it, the concentration of chloride ion is 12/4. So the hydrogen ion concentration and the chloride concentration are both 3. This is a trick question, by the way, you guys. What is the concentration of HCl? Yeah. 3? Okay, we have a vote of 3. What is your,
I was gonna say,
actually, it's 0. What? Why is it 0? Yeah, there's no HCl left. It's all dissolved or dissociated into H and Cl. Because it's a strong acid. Strong acids totally dissociate. There's nothing left. So that means the concentration of the solid acid is 0. Yeah,
so.
exactly. Now, a weak acid, perfect response. A weak acid, you've got a mixture. And you're going to get into that in 1A. Acid, in fact, you're going to get into that in 1B, actually. Because it's much more involved. You have to use the quadratic formula. The math is tricky. But with strong acids, strong bases, nothing's left. And a weak base, it depends on how strong the weak acid is. And there's something called an equilibrium constant that determines that. The equilibrium constant determines how strong an acid or base is. That's built into the calculation. But really good question. Okay, so this is going to be 0. All right. What if we had a strong acid and a strong base, dump them together? Okay, I already mentioned that's going to be a neutralization reaction. It's going to be these are all going to be aqueous. Except the water, that's going to be an L for liquid. Okay. And these are all going to be aqueous except for the water. Those are all AQs. Okay. At the point that I wrote this equation out, That means neutralization means that all the acid is used up and all the base is used up. Okay? Sometimes, though, you have leftover H's and leftover OH's. But when with perfect number of moles of H, perfect number of moles of OH, there's neither one left over. Okay, so now we need to figure out so if I dumped in um, two liters of HCl, 3 liters of sodium hydroxide, we're going to end up with 5 liters total. I want to know first of all, is this going to be a acidic solution when we're all said and done, or a basic solution? And then I want to know how much of either H plus is left over or OH minus left over. Okay, so what we need to do is calculate moles of H plus, moles of OH. So we have, say these are 3 molar. Well, let's make it different here. Okay, so we got a stronger acid than base, but we have less of a strong acid than base. Okay, first thing is moles of H. Now we know if we calculate the moles of HCl, we're going to get the moles of H. So the concentration is okay, so concentration times liters gives us moles. So this is 3. This is 2. So that's going to be 6 moles. HCl, but it's not HCl, it's H plus and Cl minus. 6 moles of each. Let's look at moles of OH. Okay, sodium hydroxide is 2 molar. And we have 3 liters of it. So that gives us 6 moles of sodium hydroxide, which is really 6 moles of sodium and 6 moles of hydroxide. Okay, remember now, reaction for water. Because once the H turns to water, the OH changes to water, they're no longer there, they're combined with the water. Okay, so we have six moles of H, 6 moles of OH. How much water did we make? 6 moles. How much H is left over? None. OH? None. So this is a perfectly balanced neutralization. So what do you think the pH of the water is going to be?
7.
It'd be 7, because 7's neutral. 7 means neither excess H is around, excess OH is around, perfectly balanced. So how many moles of salt did we make? Here's the reaction. What are the coefficients? This reaction here. 1, 1, 1, 1, right? So if we know the moles of that, we know the moles of that. If we know the moles of that, we know the moles of that. And that, actually. So we're starting with, let's just use the sodium hydroxide. What's that equal? Well, 1/1 is that goes away, right? So we made 6 moles of sodium chloride. So what we're bringing together is stoichiometry, the stoichiometry problem right here, bringing together solution chemistry, and we're bringing together acids and bases. So this unit is a culmination of the semester. It really brings everything together. Now, we can also screw this up. Instead of having these nice numbers here on the acid and base, we could change it up and actually calculate whether this is going to be a basic or an alkaline solution in the end or an acidic solution in the end. So let's do that. Okay, so we've got we have let's say one. Okay, so we have total volume of 6 liters. We dumped in 2 liters of acid, 4 liters of sodium hydroxide. And then gets really hot. Really hot. Okay, so we've got the same double replacement reaction. So first thing is, let's calculate the moles of H plus produced. So we've got, and this is all one, it's a monoprotic acid. So we've got, remember the HCl goes away. So we have, after the reaction goes, we have 0 moles, okay? So this is the initial conditions. All right, and let's look at OH. Well, it's the same thing again. Okay, so this is going to be 8 moles. Okay, now we have an imbalance of what? H's or OH's? Which is more? Yeah. Yeah, we have 8 moles of OH and only 6 of H. So after the reaction goes, we're going to make how many moles of water? And make 6 moles of water. Okay. We have 6 moles of this, the H, 6 moles of the OH. Excuse me, we have back up 6 moles and 8 moles. Okay, so the 8 moles of OH, 6 of it's going to be taken up by the 6 H's to make water. So if this is 6, this is 8, we're going to end up with 6 moles of water because we don't have enough H's to go around. So how many moles of OH is left over? 2. Okay, so this is going to be an alkaline or basic solution left over. Because we had basically more base than acid. But you have to do the moles though to calculate that first. Okay, so we have 2 moles in 6 liters. So we have 0.33 moles per liter of OH. Now, in your 1A class, you then convert that to pH. Okay, so that's a classic neutralization problem. Now, the last two labs, the two wet labs, are reading something called titration. Titration is when you mix an acid and a base together and you can calculate the unknown concentration of the base or acid. That's the essence of titration. Back in the 30s and 40s in CSI, tests, ag tests, food tests, it was all wet chemistry. 99% was wet chemistry. Instrumentation was at its beginnings, and so it was very expensive. So they used titration all the time. Okay, so that's a neutralization problem. So you calculate the moles of each one, see which one's more, and then convert that concentration.
So the number, 0.53 moles, that's, we're basically finding out how much is left over.
Exactly. Because we had more OHs, that means we had OHs left over. And you subtract the two moles together, the two molar values, and that'll give you how much is left over. Then you look at the total volume, which is now 6 liters. So you put the moles left over the 6 liters, and that's how you come up with a 0.33. So that's the molar concentration of OH.
We know that it's, alkaline or alkaline, because it's like, there's more of one.
More OHs. Yep. That's why you know it's alkaline.
It's,
Basic and alkaline, same thing as acidic. You have more H's and OHs. So those two are always present. Whenever they're present together, they immediately form water, because water is super stable. But if you don't have enough of one of them to go around, then that one's going to be left over. In this case, we had too much OH.
so H is acid, OH is the
Base.
base.
Exactly. Now, this is as tricky as it's going to get in here. Acids and bases. A neutralization problem. So, I'm going to have a take-home test or take-home problem for this test, and it'll be a neutralization problem. Give you lots of time to do it. Okay. All right, well, that's what I wanted to cover today. Are there any questions about this? If you've been keeping up in all the other tests too, this is just bringing it all together. Bringing it all together. Okay, if you go to Files and Canvas, and go to Unit 3, you'll see acid-base worksheet, dilutions, molarity, which is using dry. Lots of practice, including titrations. Okay. So that's what I wanted to cover today. Now we get to go do a fun lab.